Hello, you're welcome back to my channel, Physics with Chaos. In this lesson, we are going to consider the general properties of waves. You're welcome back. General properties of waves. What is a wave? A wave is a way of moving energy from one point to another caused by a disturbance or a vibration. Waves are made up of repeated vibrations or oscillation. You are familiar with different kinds of energy. You are familiar with light energy. You are familiar with sound energy. Okay? When light or sound is transferred from one point to another due to vibration or caused by vibration, we can say that light wave or sound wave have been produced. What causes the different types of wave, or what disturbance generates the different types of wave? For sound wave, the cause is the vibration of something, let's say my vocal cord, leading to the vibration of air particles, okay, before sound wave is produced or generated. For water wave, it is caused by an object thrown in water, a slight disturbance in water. When you throw something in water, water wave is generated. For ocean wave, a much more bigger version of water wave, this, like what we have here, this can be caused by friction between the surface of the ocean and the wind, the blowing wind. For wave in a string, it is caused by the up and down movement of a rope. So when you tie a rope to a point and start moving it up and down, a wave is generated in a string. For light wave or electromagnetic waves, as the case may be, a family of waves like gamma, X-ray, microwave, ultraviolet, infrared, and so on, including light wave, they are generally produced by a changing magnetic field. Okay, now the changing magnetic field then creates a changing electrical field. This pulse or this kind of vibration leads to production of light wave, like what we have here. Okay, so for wave in a slinky spring, like what we have here, it is produced when you move the slinky spring back and forth, okay, or up and down as the case may be. Back and forth generates a different kind of wave from the one produced when you move it up and down. Okay, now the features of waves. Guys, you need to understand that waves have a lot of features, a lot of things that are similar with them. We have the wavelength, we have the amplitude, the crest, the trough, the periods, and so on. Okay? Now for the wavelength is the distance from one point in a wave to another point in the next wave, or from one crest to the next crest. For the amplitude is the distance from the center of the wave to the crest or to the peak. Now the crest is actually the peak or the top of the wave. So when you hear a crest or wave crest, we're talking about the top of the wave. For the trough is actually the bottom of the wave. These are some of the terminologies you are going to be hearing throughout the lesson. Okay, we have the trough, the crest, the frequency. The frequency is based on the number of wave that is produced. How many wave is produced in a given time, in 1 second. Good. A wave is seen as line called wave fronts. So these are wave fronts. You have a wave front here, We have a wavefront here. We even have wavefronts. These are lines that are formed when waves are produced. They are basically called the wavefronts. Wavefronts can come in different patterns. It can come as a circular or as a plane wavefront, depending on the source of vibration. For a circular wavefront, we have something like this. It's like radiating circular. And plane wavefront will have like straight lines like this. Okay? Each of the line describes is the crest, like what we have here. Each of the line is the crest of the wave, the top of the wave, top of the wave, top of the wave, and so on. So each line here describes the crest of the wave. And between the line, we have the trough, like what you have here, the lowest point of the wave. Can you see it? Now, these are parts that are in phase, that for the lines. The parts that are in phase. Guys, the word phase, in phase, you will get to hear it in our subsequent lesson. I want you to get used to it. Parts in phase are parts that are in the same position at a given time. So we can say this crest here and this crest here, and the next one, they are all in the same position at a given time. This trough here and this trough here, they are all in the same position at a given time. Okay? So all the points in the crest in this wave, they are in phase. All the points in the trough of this wave, they are also in phase. Okay? Waves can be classified by direction of vibration into two parts. Okay? We can classify them on the transverse wave or on the longitudinal waves based on how they vibrate. For transverse wave, the direction of vibration up and down is perpendicular to the direction of the wave travel. So if the wave is traveling this way, the particle will tend to vibrate up and down here. Okay? Now for longitudinal wave, the direction of the vibration back and forth is the same as the direction of the wave travel. Okay? As the wave is traveling to my right, the particles in the wave keep going back and forth. A slinky spring can be used to model waves. Okay, depending on how you want to model it. If you move it up and down, you achieve the transverse wave, but when you move it back and forth, you get the longitudinal wave. Observe the motion of the particle of the wave shown. Now I want you to fix your eye on one particle of the wave and notice what's happening. Does the particle move towards the right or does it move up and down? Of course, it does move up and down. This shows that whenever wave travel, the particles don't travel with the wave. The particles are in a fixed, they only vibrate in a fixed position, like what we have here, up and down, up and down. The waves travel away from the source. The direction of the wave is at right angle to the movement of the source. In transverse wave, the particle do not travel horizontally. Each particle just vibrates up and down like what we have. Okay, so this is a case of a particle in a transverse wave. All the particles, how they vibrate. Good. Now let's observe the white dot there and see what happens. Observe the particle more closely and see what's happening to the white dot. What did you notice? It's going up, down, up and down while the wave is traveling. Okay, so this shows that the particle don't move with the wave, they only vibrate up and down in a transverse wave. Examples of transverse wave are these: water ripples, light wave, wave in a rope or a slinky spring, depending on how you move the rope or the slinky spring. If it's up and down, then you have a transverse wave. The earthquake, the seismic S wave, all electromagnetic wave, okay, they are all transverse wave based on how they vibrate. Okay, what are the parts of the transverse wave? These are the parts of a transverse wave: the peak or the crest, the trough. Okay, the peak and the trough. Now the S wave, that is a seismic S wave, is actually a secondary wave produced by earthquake and is transverse, which shakes the earth from side to side. Okay, so seismic wave, we mentioned it earlier that it's a transverse wave. Okay, now wavelength of a transverse wave, I've already discussed this earlier. I said the distance from the peak of the wave to the next peak, or the distance from one point on the wave to the next point on the next wave produced, or a similar point on the next wave, whichever, or the distance from the trough to the next trough. We can use the symbol lambda, this symbol here, to represent the wavelength. Amplitude of a transverse wave. The amplitude is the distance from the center of the wave to the peak or to the top, or from the center of the wave to the trough. That represents the amplitude. The higher the amplitude of the wave, the more energy carried by the wave. Okay? Frequency of a transverse wave. The frequency of a transverse wave is actually the number of waves passing through any point in 1 second, or the number of waves produced in 1 second, or the number of vibration made that produces the wave in 1 second. So we can say frequency is the number of waves passing through a point over time. Okay, the unit for frequency is actually the hertz. So a wave of 1 hertz will have 1 wave per second. Of course, a wave with 4 hertz, we have 4 waves per second. You can identify the number of waves by counting the peak. Okay, make sure that it's equal to the trough. For instance, 1, 2, 3, 4. Here it's equal to 1, 2, 3, 4. So in this case, I have 4 waves passing through a point in 1 second, or 4 hertz. What do longitudinal waves look like? A slinky spring can be used to model longitudinal wave when you move it back and forth, but you need to attach it to a point. So when you move it forward, it forms a region, which is otherwise called the compression region, this region. When you take it backward, it spreads out the spring. Okay, so we can actually use this to model how a longitudinal wave look like. The compression region is the region where all the springs are in high pressure. They are all compressed to each other. While the rarefaction region is the region where all the waves are separated. All the springs are like separated from each other. Okay, they are in low pressure. Okay. Now we need to know that the P wave, the P seismic wave of the earthquake, is a longitudinal wave, and it behaves like this. It moves the earth, push and pulls the earth whenever it's produced. Longitudinal wave. Sound is one good example of a longitudinal wave. Now notice the back and forth movement of this speaker. The forward movement pushes the particles together, while the backward movement separates the particle, and the sound wave travels to the air. Notice that even in the air we have particles, so these particles tend to vibrate too. Okay, now the vibration of the particle is transferred to the eardrum, which vibrates in sympathy or in a similar way as the particle vibrates. Okay, and then these are transferred to the ear ossicles, and then to the cochlea, where we have liquids that also vibrate, and then the signal in the liquid are transferred through nerves to the brain as electric signals. Okay, but I want you to fix your eye on this. notice what happened to the particle, this red dot right on the spot. How is it vibrating? Notice it's going back and forth, back and forth. So it means the particles of air, whenever sound wave is produced, only move back and forth. They don't move along with the sound wave. They only vibrate on a spot. Good? Now, fix your eye on this red dot, and that will help you to understand this concept better. Now, notice that the white dot keep going backward and forward. The forward vibration makes it pushes it, while the backward vibration loosens the whole thing. Okay? So sound is an example of a longitudinal wave. Other example is a seismic P wave and a slinky spring moved back and forth. Wavelength of a longitudinal wave. To figure out the wavelength of a longitudinal wave, you need to find out the region of the compression, the middle of the compression, and the middle of the next compression. That's a wavelength. The distance from that middle to the next middle of the compression. Or you need to find out the middle of the rarefaction and the middle of the next refraction. So the distance is the wavelength. Good? The symbol lambda is used to represent the wavelength. Now this is a simple representation of sound wave using lines. The lines that are closer together shows compression, and those far apart shows rarefaction of the wave. Now, in summary of transverse and longitudinal wave, we see that the particle here vibrates up and down, while the particle here vibrates back and forth as the wave travels towards the right hand side. Good? Wave properties. In the laboratory, we use the ripple tank to study wave properties. This is a ripple tank. It has a vibrator or a dipper, a water surface, a shallow tray, and so on. Now, when the vibrator is dipped, a wavefront is generated, or a wave is produced, depending on whatever is being dipped. Sometimes a circular wavefront is produced, depending on this. If this is being dipped, something that is sharp or circular, then you have a circular wavefront. Now, the properties of wave can be studied from the ripple tank. Some of the properties of wave are similar to the properties we've gone through in light wave. Of course, light wave are also waves. So these are just the general properties that applies to all wave. We have the reflection of wave at plane surface. So that's one. Number two, we have the refraction, which is the change in direction of wave caused by changing speed. We have the diffraction, okay, how the wave spreads out. And then we have the interference, which is adding up or cancelling out. There are, however, other properties that doesn't apply to all waves, like polarization. Polarization applies to transverse wave only, so they are not mentioned here. Reflection. Let's say a plane wave is produced in a ripple tank and it travels. When it comes across, hits an obstacle that is placed at an angle, it reflects at an angle. So if I should draw a demarcation here to represent the normal, then the angle of incidence of the wave and angle of reflection of the wave will be equal. Okay, so this is a demonstration of reflection. But if this obstacle is straight, it reflects back to the source. This is an idea of the reflection of wave. Good? This is an idea of the reflection. So wave coming in, hits an obstacle, boom, and then move back at an angle. Good? So the angle of incidence and the angle of reflection of the wave will be equal. Refraction. Now, if you have a wave generated, a plane wave generated in a ripple tank, then you decide to place a plastic item, a piece of plastic inside the ripple tank to create a shallow region. Now, as soon as the wave gets to the shallow region, the speed changes. So if it's moving very fast, the speed decreases once you get to the shallow region. Okay, but if that obstacle is kept at an angle like this, the speed don't just change, the direction also change. Okay, see the wave moving. Once you get to that region, the shallow region, the speed decreases as well as the direction changes. Now notice that the wavelength is distance from one line to the next line. Notice that the wavelength here is even smaller at the shallow region compared to the deep region. Okay, diffraction. Whenever a wave gets to an obstacle, okay, it spreads out. This can be demonstrated in a ripple tank. So a wave, let's say a plane wave is produced in a ripple tank, and you kept two obstacles in the part of the wave gets to spread out quickly. Now the best spread is observed when the length of the gap is equal to the wavelength of the wave produced. Okay, so if the gap is too wide, the spread would not be as much, and if the gap is too small, there would not be any spread at all. So this is the best spread that you can get. The length of the gap is similar to the wavelength of the gap. Okay, so this is a clear demonstration of what's happening. There are other cases of diffraction like this. These are other cases of diffraction of other kind of waves, electromagnetic waves. Good, light wave and so on. These are other cases of diffraction. Guys, I believe you will enjoy the video. Please don't forget to like, share,